Good day, everyone, and welcome to the Series 2 of our Engineering Algebra 1 revision titled Boolean Algebra. I'm Dr. Oluwafemi George from Systems Engineering Department, University of Lagos. Boolean Algebra. The ideas of Boolean variables and expressions are crucial in computer science and mathematics because they deal with logic and binary values. In the 19th century, a mathematician constructed an algebraic logic system, and Boolean algebra has been named after this mathematician, that is, George Boole. Boolean algebra, also known as logical algebra or binary algebra by definition, is a kind of algebra in which the variables values are the true values, that is, true and false, which are normally expressed as 1 and 0 correspondingly. It has various applications, such as in the analysis and simplification of digital circuits or digital gates, as well as in statistics and set theory. It was also crucial in the creation of digital devices and is supported by all current programming languages. Basic operations of Boolean algebra include conjunction or AND operation. The AND operation is a fundamental operation in Boolean algebra that returns true 1 only when both operands A and B are true. In other words, it is true if and only if both inputs are true. If we look at the table, we will see that the AND operator only returns true, that is 1, when both A and B are true, or 1. Disjunction or OR operation. The OR operation returns true, that is 1, if at least one of its operands, A or B, is true. In other words, if it is true, that is 1, if any of the inputs are true. In the truth table shown, we can say that the outcome is true 1. That is, if at least one of the inputs is true. Then we have negation or NOT operation. The NOT operation negates the value of its operand A. In other words, it transforms true, that is 1, into false, and false, that is 0, into true, as shown in the truth table. In addition to AND, OR, and NOT operation, we also have the NAND operation that stands for NOT AND returns true, that is 1, unless both operands are true. The NOR operation is the negation of the OR operation and returns true only if both operands are false. XOR operation is also known as exclusive OR. It returns true, that is 1, if exactly one operand is true. Otherwise, it returns false. We also have the XNOR operation, and this is the negation of the XOR operation. It returns true, that is 1, if both operands are equal, that is, either both true or both false. Laws guiding Boolean algebra. There are some laws guiding the use of Boolean algebra, and they are the identity law for OR and the identity law for AND. The identity law for OR states that combining any Boolean variable A with false O or 0 using the OR operation results in the original variable A. While the identity law for AND states that combining any Boolean variable A with true 1 using the AND operation results in the original variable A. We also have the domination laws for OR and for AND. The domination law for OR states that combining any Boolean variable A with true 1 using the OR operation results in true, that is 1. And the domination law for AND states that combining any Boolean variable A with false O, 0, using the AND operation results in false 0. We also have the idempotent laws for OR and for AND. The idempotent law for OR states that combining a Boolean variable A with itself using the OR operation results in the original variable A, while the idempotent law for AND states that combining a Boolean variable A with itself using the AND operation results in the original variable A. We also have the complement laws for OR and for AND. The complement law for AND or for OR operation states that combining a Boolean variable A with its complement using the OR operation results in true. The complement law for AND states that combining a Boolean variable A with its complement using the AND operation results in false. For the commutative law for OR operation can be expressed as A or B is equal to B or A by swapping the positions of operands A and B in an OR operation without changing the results. Similarly, in the commutative law of the AND operation, you may change the places of operands A and B in the AND operation without altering the results. Associative laws. For the OR operation, the associative law can be expressed as A or B or C equal to A or B or C, meaning that you can group the operands A, B, and C in any way you like within the OR operation, and the result will be the same. For the AND operation, the associative law can be expressed as A or B or C equals A or B, A and B and C equals A and B and C, implying you may change or you may arrange the operands A, B, and C in any manner you choose inside the AND operation and get the same result. We also have absorption law for OR and AND, simplification law for OR as well as for AND, distributive law for AND over OR as well as distributive law for OR over AND, first and second De Morgan's law, and so on. Now, let's look at canonical forms of Boolean expressions. In Boolean algebra, there are two canonical forms that Boolean expressions can take. We have the sum of products, that is SOP form, and the product of sums POS form. So in the table shown, the output is F, and it returns 1, 0, 1, 1, 0, 1, 1, and 0. So now we are going to write the expression for F using the sum of products and as well as using the product of sum. So in the first case, F of A, B, C is equal to, so to do this, we go to the truth table where we have 1, where the output gives us 1. Let's take note of where we have the cell with output as being 1. So that's 2, 3. We have about 4 places, cells with output as 1. So for the first one, A is 0, B is 0, and C is also 0. So we have A, B, C. So because A is false. So we have A bar, B is also 0. We have B bar, and C is also 0. We have C bar. For the next one, we have A, B, and C as well. But A is 0, so we have A bar. We have B as 1, so that stays. Then C is also 0. We have C bar as well. For the next one, we have A, B, C. So A is 0. We have A bar. B is 1, so it remains the same. Likewise, C is 1, so it will remain the same. Then the next one, we have A, B, and C. A is 1, it remains the same. B is 0, so we have B bar. Then C is also 1, so it remains the same. The last one, we have A, B, C also. Here, A is 1, it remains the same. B is 1, it remains the same. C is 0, so we have the bar. So the sum of products means that we find the product, then we sum. So in this case, the sum of product F of A, of B, of C is A bar, B bar, C bar plus A bar, B, C bar plus A bar, B, C plus A, B, C, B bar plus the last one, which is A, B, C bar. So now, to find the same for the product of form, which is F, the outputs A, B, C. So this gives us, we look at the 0 where we have 0. So we have 0 here. We have 0 here also. We have 0 where the output is 0 here. So this one is A, B, C. A, B, C. Then we have A is A plus B plus C. Actually, A plus B plus C. And here it should be A plus B plus C. And this one should be also A plus B plus C. So if you look at the first one, A is 0. So because the output is also 0, A stays the same. B is 0, it stays the same. C is 1, then we have C bar. If you look at the next one, A is 1. Because the output is 0, so A will carry bar. B is 0, it stays the same. C is 0, it also stays the same. Then the last one, A is 1, so it carries the bar. B is 1, it also carries bar. Then C is 1, it carries bar as well. So now, the product of sum for this expression is now A, let me write it here, F of A, comma B, comma C is equal to A plus B plus C multiplied by, because now we are dealing with products of sum, A bar plus B plus C multiplied by, again, A bar plus B bar plus C bar. And that is our expression for the product of sum. Now, let's look at the construction of Canonical maps and see how to use them to simplify Boolean expressions. Canonical maps are visual aids for simplifying Boolean statements and are especially handy for expressions containing several variables. So the number of cells needed in K-map for a Boolean statement with n variables is 2 raised to the power n cells. For example, the number of cells in the 2-variable K-map, if variable is n is 2 for a 2-variable K-map, the number of cell is 2 raised to the power 2, which is equal to 4 cells. So how do we construct this? So we can construct this way. So let's say this is A and this is B. This A returns 0 and 1, and B also returns 0 and 1. So for AB, for the binary AB, we can have 0, 0 combination, 0, 1, 1, 0, and 1, 1 combination. So this takes the first cell, this takes the second cell, this takes the third cell, and finally this takes the fourth cell. So we can label the cell position as 1, 2, 3, and 4. This is for 2-variable K-map. Now let's look at 3-variable K-map. For a 3-variable K-map, so we have 2 raised to the power 3, which is 8 cells. So now let's construct the cell. Let's say this is our A, and we have BC here. So we can see that we have 8 cells. So A, we take 0 and 1. So how do we distribute BC? So to distribute the BC, this convention should be used. We have 0, 0, 0, 1, 1, 1, and 1, 0. So this takes position 0, position 1, position 2, and position 3. So meaning that here we have 0, 0 here, we have 0, 1, we have 1, 1, and we have 1, 0. So now, but we have 3-variable K-map, so we need to construct a table for A, B, C. So for A, B, C, so we have 0, 0, 0, we have 0, 0, 1, 0, 1, 0. We have 0, 1, 1. We have 1, 0, 0. We also have 1, 0, 1. We have 1, 1, 0. Then we have 1, 1, 1. So we label this as cell 1, 2, no, 0, 1. I beg your pardon. 2, 3, 4, 5, 6, and 7. So that determines the numbering here. So where we have 0, 0, 0, this takes 0 position. This takes 1, 0, 0, 1, 0, 1, 1. The next is 0, 1, 0. So 0, 1, 0 is here. So it will take 2. Then we have 0, 1, 1. It will take 3. We have 1, 0, 0, which we take 4. We have 1, 0, 1, which is we take 5. We have 1, 1, 1, 1, 0, which we take 6. Then finally, we have 1, 1, 1, which we take 7. Now, let's look at these solve examples. 1. Generate the sum of products or product of sum for f of A, B, C in the two tables shown below. So the first thing we need to identify for the sum of products, we identify where the output, it says solution. So the first objective is to find SOP for f of A, B, and C. So now we identify where the outputs returning 1. So we have 1, 2, 3, 4, 5, 6, and 7. So in this case, we have A, B, C. But because A is 0, B is 0, and C is 0, so they carry bar, A bar, B bar, C bar. So the next one, A, B, C also, because A is 0, we have A bar, B is 0, we have B bar, but C is 1, so still remains. For the next one, we have A, B, C as well, but A is 0, we have A bar, B is 1, it remains, C is 0, we have C bar. The next one, A, B, C as well. A is 0, we have A bar, B is 1, it remains, C is 1, it remains. Then the next one, we have A, B, C. Because A is 1, it remains, B is 0, we have B bar, and C is 1, it remains. Then the next one, we have A, B, C as well. Because A is 1, it remains, B is 1, it remains, C is 0, it carry bar. Then the last one, we have A, B, C. Because A is 1, B is 1, and C is 1. And so the results, sum of product we are looking for, SOP, is A bar, B bar, C bar, plus A bar, B bar, C, plus A bar, B, C bar, plus A bar, B, C, plus A, B bar, C, plus A, B, C bar, plus A, B, C. So that is for the sum of products. Now, for the product of sum, which is POS, so F of A, B, C. So now we only have one cell that is returning 0. So for this cell, we know A plus B plus C. Because A is 1, so A will carry bar, B is 0, B will remain, and C is 0, C is remain. The idea of product of sum is to provide a faster way of estimating the output. Because instead of summing A, B, C in 7 cells, so we can just estimate the outputs using the product of sum. And that corresponds to just one cell that returns 0 as the output. So in this case, our product of sum is A bar plus B plus C. Now, we have to solve F of A comma B equals 0, 2, 3. Solution. So in doing this, we want to construct Canonical map to solve this problem. So let's draw our Canonical map for the 2 by 2 variable K map. So let's call this A and this B. So A is 0, 1 and B is 0, 1. So AB will return 0, 0, 0, 1, 1, 0, and 1, 1. So these are the possibilities. And this takes 0 cell. This takes cell 1, takes cell 2, and this takes cell 3. So we can label the cell as 0, 1, then 2, then 3. Now, F of A comma B equals summation of 0, 2, 3. So wherever we see 0, we put 1. So we can see 0 in cell 1. So we put 1. We can see 2 also in cell 2. So we also put 1. Wherever we see this value inside this summation, we put 1. So also we can see 1, 3. We put 1 in cell 3 because it's also part of what we are looking at. So to solve this, we can take this 1, 1 together like this. We can term this equation 1, or we can also take this cell like this, where we have the 1 and 1, then we can term it equation 2. So the idea is to solve for equation 1 and equation 2, then the output will be the summation of the result in equation 1 and in equation 2. So for 1, we have A, B, A, because we have 2 cells, so we have AB plus AB. So for the first AB, A is 1 and B is 0. So B is 0, that means we have B bar. So for the second one, that is cell 3, we have A is also 1, B A is 1 in cell 3. Likewise, please, pardon me, this will be 1. A is 1 in cell 3, and B is also 1. So this remains the same. So now, this B bar, we cancel this B to give us A. Because we have AB bar plus AB, so this is the negation of B. So we cancel, so we have A. Then for the second equation, which is 2, also AB plus AB. So in this case, A is 0 and B is 0. So A is 0 and B is 0. For the second cell, we have A is 1 and B is 0. So we have A, B bar. In the same way, we have A and the negation of A cancelling each other. So, and this gives us B bar. So the output that we are looking for, our output is now equation 1 plus 2, which is A plus B bar. Now, let's look at another example. F of A comma B is equal to summation of 0, 2. And we are still on 2 variable K map. So let's construct the K map table. We have A here, which is 0, 1. We also have B here, which is 0 and 1. Then we have the A, B, which we have as 0, 0, 0, 1, 1, 0, and 1, 1. This will take cell 0. This will take cell 1. This will take cell 2. And this will take the third cell. And the cell is labeled this way: 0, 1, 2, and 3. So in this case, where we have 0 and 2, in the Canonical map, we put 1. So in cell 0, we put 1, and in cell 2, we also put 1. So now we can solve this together because we have 1, 1, then, or we can also treat the 1 individually. So in this case, let me treat the 1 individually. Let's call this first one. Let's label it equation 1. And let's label this second one. Let's label it equation 2. So for the first one, which is our equation 1, it is A, B, but A is 0, which is bar, and B is also 0, which is bar. So for the second one equation, A, B, we have that A is 1 and B is 0. So we have A, B bar. So the output of this expression is A bar, B bar plus A, B bar. And this gives us, because we have A and the negation of A, which cancel each other, and this gives us B bar, as we can see. Now, let's look at the 3 variable K map. Let's look at this 3 variable K map. F, A, B, C equals sum of mean of 0, 2, and 6. So because we have 3 variable K map, we have 2 raised to power 3 number of cells. So we need to draw the cells first. trying to draw the cell. So now this is A and this is BC. So this returns 0. We have this possibility. Then for the BC, we know that BC, we can either have 0, 0, 0, 1, 1, 0, 1, 1, and 1, 0. So this goes to cell 0, this goes to cell 1, this goes to cell 2, and this goes to cell 3. So we have it here as 0, 0, 0, 1, 1, 1, and 1, 0. We also need to construct for the three combination A, B, C. A, B, and C. We know that 0, 0, 0, these possibilities, you can have these possibilities 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And from here, this takes 0 cell 1, 2, 3, 4, 5, 6, and we have the 7th cell here. So we can label this cell. This will be 0, 1, 2, 3, 4, 5, 6, and 7. So wherever we have 0 to 6, we put 1. So we have 1 here, we have 1 here, then we have 1 here. So now, to solve this, we can combine these two ones together. We can call this equation 1. Then we also have 1 here. We also have another one here. So we can also combine this and call it equation 2. So for equation 1, we know that because we are dealing with two cells, so we can write ABC twice. First, ABC. So this one is A bar. If we solve from 2 down to 6, we have A bar, then B is 1, and C is also 0, which is what? C bar. Then the second one is A. A is 1, as you can see. B is 1 also, then C is also bar. So this gives us, we have A and A bar, so these cancel each other. We have B, C bar. So for the second one, we also have A, B, C plus A, B, C. So if you look at the first one is A is 0, which is A bar, B is 0, which is B bar, and C is 0. Then for the second one here, which is A is 0, which is A bar, B is 1, so it remains the same, then C is 0, which is C bar. So this one also returns, we have B bar and B. So this gives us A bar, C bar. So our output is now B1, equation 1 plus equation 2, which gives us B, C bar plus A bar, C bar. Now, let's look at this last example, f of A, comma B, comma C equals 0, 2, 4, and 6. So here, we need to construct the Canonical map. And to do that, I'm going to do that now. So we have A, we have B, C. So as we have done before, we know this is 0, 0, this is 0, 1, this is 1, 1, and this is 1, 0. This is 0, 1, and this is 0, 1. This is 0, 1, this is 2, and this is 3, 4, 5, 6, and 7. So when we have 0, 2, 4, 6, then we put 1. So we have it here. So this is 1. This is 1 here. This is 1 here. And this is 1 here. So we can solve this by grouping these two at the same time. Call this equation 1. Then we group this one also together. Then we call this equation 2. Then for the first one, I is equal to ABC plus ABC, because the A is 0, B is 0, and C is 0. So we have A bar, B bar, C bar. Then here also we have A, B, C. A is 1, B is 0, we have B bar, then C 0, we have C bar, and this returns because A bar we cancel A, and this gives us B bar, C bar. Likewise, for the second one, we have A, B, C plus A, B, C. A is 0, we have A bar, B is 1, then C is 0, we have C bar, plus A is 1, B is 1, and C is 0, we have C bar. And this gives us A also we cancel, A bar we cancel A, we have B, C bar. So our output is equal to B bar, C bar plus B, C bar, and this gives us, because we have negation of B and B, and this gives us C bar.